Welcome, everyone. I hope you can hear me. We're about to begin. Thank you for coming to our quantum computing seminar series. And today it's a special event for us because we're typically going over the algorithms and proofs, but today we're going to shift gears and Ian Morris is going to present a tutorial, which could be a great way for those of you who have never seen quantum computing to learn more about it. So we're still waiting for a few people to join, but I just wanted to just let you know that we are a group that's associated with the Quantum Science and Engineering Center. And so I will put a link here in case you want to learn more about us. And you have never seen this in any of the emails, probably by now everybody is familiar with it, but there are a lot of quantum related activities going in the center, and the quantum computing is just one of the groups in the center. We also have people doing material science and sensors, quantum sensors. So there are a variety of different things that you could be part of. But I wanted to also tell you another opportunity. If you're interested in learning more about computing, there are courses currently being offered as part of the physics and math curriculum that could be a great option for those of you who want to do more quantum related things in the future. There is an undergraduate and a graduate version of those courses. They're being at the moment taught on a yearly basis, but you will have an opportunity to do it next fall, for instance, if you haven't signed up already for one of these this fall. But send us an email if you are interested in taking those courses. We'll send you a syllabus and talk more about it if you'd like. So let me just, by the show of hands, so we're still maybe a couple of minutes before we begin the actual presentation, but can you tell me if, so in the participant window, you have an opportunity to say yes and no to the questions that I'm asking. So how many of you are undergraduate students? Okay, so, and I'm still admitting people, so this is not the, okay, so how about graduate students? A few grad students, great. Faculty or people from industry? Okay, a few. Okay, great. Wonderful. So it's great to have a diverse crowd. I will stop sharing this advertisement for the talk, and I just wanted to say a couple of words about Ian. So Ian is an undergraduate student in the physics department. He has been working with Ming Tian and I on a research project related to computing this summer. He is going to talk to you about Qiskit, which is a platform that, as you saw in the ad for this event, is very accessible, and it should be easy to start. It's probably even easier than MATLAB, but it also will give you a glimpse of what quantum computing with quantum circuits looks like. So without further ado, I will let Ian share his screen and talk to you about Qiskit. But if you have questions at any time, feel free to put them in the chat. I will also record this, and I will make this available for those of you who need to go over this again at your own pace later on. So feel free to just request that at any time later. But I'll try to moderate the chat, and if you have questions that you want to ask Ian, I think, Ian, if you don't mind, maybe we can just let people unmute themselves and ask. Is that okay with you?
Yeah, that definitely works. And I was going to say similar things that, if you don't want to unmute yourself, you can just put it in the chat, and maybe if Maria, you could just pass that along.
Absolutely.
That would work. Great.
Yeah. So any questions before we begin? Anything? Okay. So it looks like we have a good crowd already, so we should get started. And Ian, please take it away.
Yeah, so before I share my screen, thanks for the introduction. I'm a senior physics undergraduate working with Ming Tian and Maria Emelianenko. So today I'll be talking about Qiskit, which is a software development kit created by IBM to increase access to quantum computing research by letting people around the world have access to real quantum computers as well as simulated versions of quantum computers. So my talk will cover basically the basics of Qiskit, and hopefully give the audience a good understanding of how to navigate it so they can go out and start using Qiskit for themselves. Due to time constraints, I will not be able to comprehensively cover every aspect of it. So some of the more advanced topics like the circuit library and application programs that Qiskit provides will not be covered, but Qiskit provides excellent explanations for such things, and they have YouTube videos, they have a free textbook, and I'll showcase these things. So anyone interested should be able to look into that, and that should more than supplement any information I don't cover. So yeah, I can start sharing my screen now. Yeah, so let me just. All right, so everyone should be able to see my screen now. And let me know if you're not able to. But so to begin the presentation, I'm going to do it in maybe a more unconventional style, but which I think will work for this topic. So instead of showing a classic PowerPoint with slides, I'm going to work directly from the Qiskit website. So I hope that will make it as easy as possible for the audience to get comfortable with the environment that they would be working with, and should they choose to use Qiskit, so that afterwards those who are interested can start immediately implementing. So just from the outset, starting from any search browser, if you type in IBM Qiskit. Oh, actually, if someone could mute themselves, I hear some static.
I think it. I just muted. Maybe it was Javier.
Okay. But yeah, and actually, yeah. So starting from any search browser, if you type in IBM Qiskit, just doesn't matter which one, and you click on qiskit.org. That's basically where you're going to start your Qiskit journey. So it's just sort of a basic introduction. The primary place we're going to look at is the quick start area. Basically, there are two avenues to getting started with Qiskit. One is starting locally, where you can download it with like Python 3.5, and they recommend using Anaconda, which is just a virtual environment that you can use Python, or yeah, that can use Python. The second route, which we'll be going through and exploring more in depth, is the IBM Quantum Experience, which is basically IBM's Jupyter notebook, which lets you get coding and using Qiskit right away. This is probably the easiest way to get started for those who just want to sort of dip their feet in the water. And this is also, yeah, the path that we'll be explaining in this presentation. So to use the IBM Quantum Experience, you do need to create an account. So when I click on the start button, it'll just go to my account. But if you don't have one, you'll have to create one. But it's free, so that it shouldn't be an issue. You can create one really easily. I will mention that there is a premium version of the IBM Quantum Experience, which lets you access more quantum computers that have more qubits. But if you're just starting out, you really don't need that, and the free version has more than enough for what you could want. So just clicking on the IBM Quantum Experience. So the first screen you'll see is just sort of the initial interface. It'll show you recent circuits that you have right here. And actually, let me try the annotate feature to try, and I wonder if I can use a laser pointer. Okay, actually, no, I won't try that. But so yeah, the initial interface, it shows basically. It shows the circuits that you have, and then on our right, you can see the real quantum computers as well as. Oh, actually, I think I need to stop using annotate. But yeah, on our right, you can see the real quantum computers as well as the simulator versions. So here's the simulator that you can run your circuits on, but in general, all of them are live quantum computers. And so the information that it provides just off the top, it provides a queue. So this is the number of jobs that are currently being run. So let's say you wanted to run a quantum circuit, you would just run it, and then it would say that there has been a job added, and so it would increase by one. And it also tells you how many qubits you have access to. So if you just click on it, it shows you the qubits you have access to. So in this case, it's 5, as well as the connectivity between them. So if you're trying to do a C0 between 0 and 2, you wouldn't be able to do that, and you would have to like do some swapping operations because 0 and 1 are the only ones that are connected. So you can only perform 2 qubit operations between qubits that are connected with like arrows. It also tells you the error rate between qubits. So in this case, the single qubit for any single qubit gate, the error rate is shown here, and the C0 error rate is shown here. But yeah, it gives you some basic information about the quantum device itself with 5 qubits. It talks about how, how long it's been online, as well as the maximum number of shots that can be used. And so the shots is just how many measurements you can take of one circuit. And so that's important for sort of developing a probabilistic understanding of the circuit in terms of, what state is it in various things. It also tells you what sort of gates you can use. So in this case, it gives you access to basically all the single qubit gates, as well as a C0 gate, the identity gate. And so that just kind of tells you exactly what you can use or what you can do with that computer. So yeah, so that's basically that. One last thing though to mention is that the names of the devices, so in this case, Santiago, will come in handy when you're choosing which device you want to run your circuit on. And so that would be either through the circuit composer, which I'll show later, or the quantum lab. And so the way it ultimately works is you would choose a backend or one of these devices to run your circuit on, and you would call that backend. So in this case, Santiago, and that's how you would basically choose which one you want to run. So the next part is this sort of interface. So you have the results page, which these 3 things I'll go over at sort of the end of the presentation. But the part that I want to focus on first is this docs area, which is under resources. And so this is basically the place where you'll be spending most of your time, because it has all the information you could possibly want. So if you're a complete beginner to quantum computing, or if you're really advanced, this basically has everything from the very basics to like the most advanced topics. And so for anyone who's interested in learning more about Qiskit after the talk, they can just go here, and this is where they'll find most of their resources. So just to highlight at the top, they have a what's new section that basically gives you a month by month play-by-play of like what has been added to Qiskit. So in this case, it gives you sort of like updates and new features that Qiskit has added. But the place we'll start first is sort of the heart of Qiskit, and basically the coding of your first quantum circuit. So at the top, it can be sort of making circuits can be broken down into 3 basic steps. There's the build phase, where you're actually designing the quantum circuit that represents the problem you're considering. The next step is, after you've built your circuit, you would run it on different backends. And in this case, a backend is a system or a simulator. And so the system would be an actual quantum computer that has access to like real qubits, whereas a simulator would just be a classical machine that can run your circuits. The next step would be analyzing the results. So, using statistics and visualizing the circuit, so you can like look at the circuit diagram, or you can produce a histogram of the probability of which state it's most likely to be in when you measure it. So to start, they go through the steps. So you would sign in. So I've already done that process. The next part would be going to the quantum lab, which is on your left here on this interface. In this case, we'll just follow this example, but when you go to the quantum lab, it's going to give you the option to create a new notebook. And so that's where Jupyter Notebook comes in handy, where you're going to be coding in Python, but using the methods that Qiskit provides. And so you would run your code there, and I'll show some examples later on. So the first part just is like your first code. So this is just an example circuit, but it starts out, you have a circuit and you set it equal to quantum circuit. So this is what all circuits would be called. And then the first argument is the number of qubits that you want. And then the second argument is the number of classical bits. So in this case, it's 2 qubits. and 2 classical bits. And so the next step after you've created the circuit is just adding gates. So for those of you who are familiar with quantum computing already, you can basically add any gate that you might want onto it. So for a Hadamard gate, you could, this is what the Hadamard gate is represented by. And so it's a single qubit gate. So you would enter this, and then you would enter the qubit that it's supposed to be acting on. So in this case, it's 0. So for 2 qubits, the way that those are represented would be 0 and 1. For 3, it would be 0, 1, 2. That's just the naming scheme that they went with. And then, the next gate, maybe you want to add on a CX, or in this case, it's a C0 gate. The first argument is the control qubit, and then the second argument is the target qubit. And you can basically generalize this to any control gate you want. So, if you wanted a CH or a control Hadamard gate, it would be a CH, and then this would be the control bit, and then the target qubit. So after you've created, this is sort of like you create the circuit, you add gates to the circuit, and then you want to make some measurements. So the way this works is the first argument is an array of the qubits that you want to measure. So in this case, we want to measure the 0th qubit, or the first qubit, and then the 1 qubit, which is the second qubit. And then the next argument is the classical bits, which you would be mapping the measurement onto. So in this case, it would be mapping the 0th qubit to the first classical bit, or the 0th bit, and then the 1 bit, or the 1 qubit goes to the 1 bit. And then after you've done the measurement, this is where you would use the simulator. So the simulators and backends come through what Qiskit calls AIR. And so you use the method air.getBackend, and this is where you would name the thing that you want to run your circuit on. So in this case, they're using the simulator, which isn't an actual quantum device. It's just a classical device. But it has up to 32 qubits, and it will do all the operations you want. So it's totally sufficient. And so after you've chosen the simulator, you would specify the job, and that's going to execute the circuit. And so the first argument is just the circuit that you want to execute the measurement on. Then you choose the backend, which is simulator, and then this is the number of times you want it to be measured. So in this case, they've chosen the shots to be 1,000, but it could go up, and I think on the initial interface, it shows how many shots maximum each device has. So I think for the simulator, it's like 8,000, but they're keeping it smaller with just 1,000. But that's just how many times the circuit will be executed to get sort of like the end state. And then once that job has been instantiated, you can get the results from it by just using job.result. And then the next part is just getting the counts. So in this case, the counts would represent basically how many times was the quantum state in the 0, 0 or 1, 1 state. And so it'll print out, in this case, the number of times that it was in the 0, 0, where both qubits are in the 0 state, was 482 times out of 1,000. And then the number of times that it was in the 1, 1 state, where both qubits were in the 1 state, was 518. And then here's a drawing of the circuit using the circuit.draw method. And I'll go over the sort of visualizing stuff a little bit later more in depth, but this is just a basic way to represent the circuits. And so you have the initial Hadamard, which we applied first on the first qubit right here. And then you have the control X, or the control NOT gate. And that's just the control qubit is represented by this black dot. And then the target qubit upon which the NOT gate is acting on is represented by this. And then there's a line connecting them. And then the measurements are represented by these M's connecting, basically mapping to which classical bit it's supposed to be measured on. So in this case, the first qubit is mapped onto the 0th classical bit, and the second qubit is mapped onto the first one. So after getting the shots, this form of like visualization isn't necessarily the most helpful in terms of understanding the probability of like what probability the state is in 0, 0 or the state is in 1, 1. So that's where they have you can plot a histogram of it. So in this case, you just use the plot histogram method, and you take the counts value, which we defined above as from the result. And so after doing that, you can, once you plot it, it gives you a pretty basic, 0.482 because it's 482 over 1,000, and then 0.518 because it's 518 over 1,000. And so now, they go into a more in-depth explanation. So before, like when you first create a notebook to run a circuit, there's a bunch of stuff you have to import. And when you actually go into and create a notebook, all of this should be already imported. But if you don't have it, then you can just copy paste this. And throughout all of these like tutorials on Qiskit, all of the code blocks are amenable to, you can just copy paste it and put it in your own code. So in that way, any sort of information that Qiskit provides, you can also easily implement on your own by just copying and pasting. So yeah, it basically just goes through, what a quantum circuit is, all the stuff that you're importing, and the various things, the various information provided there. So yeah, so the first part is you create your circuit, the quantum circuit. So already went through that. And then the next part is basically adding gates. And then after that, you've simulated the experiment. So basically just goes through what I've just done. But this is just sort of like to show that all of the information that I'm going through, you can find for yourself, and they have detailed explanations. So if there's anything that's not clear or anything, Qiskit provides a lot of information regarding that. So the next part of this is going to be the quantum. Yeah, so I've got a tutorial circuit. So at the top, we see this is what all of your Quantum Lab notebooks are going to look like. So at the top, it has the basic Qiskit cell. And so this is what I just showed, but it's basically, it imports all the things that are necessary. And so the way you would work this is you would run the first cell, and then it like imports and does all that. And then the next part would be you create a quantum circuit. So in this case, the quantum circuit is 3 qubits and 3 bits. So you would run that cell, and then it would basically actualize or instantiate the circuit. And then the next part is adding the circuit gates. So in this example, we have a Hadamard gate, a C0 gate, another C0 gate. In this case, the control qubit is the 0th one, and the target is the 2nd one. So you would run that, and it doesn't, when you do this, it doesn't print anything out. But then when you do the draw method, and again, I've got another set of information that kind of goes through more in depth. But in this case, the draw method is a little bit more complex because it's using matplotlib's representation of it. So this is what it would look like. So you have the Hadamard gate, you have the control NOT gate acting on the first qubit and the second qubit, and then the control NOT gate on the first and third. The next step is just importing the backend. So in this case, we want to use the state vector simulator. And so this simulator basically will show you the coefficients for each state. So that kind of gets to the next part where you do the job and you do the result, and then you can get the state vector using the results. So instead of result.getCounts, we would be doing get state vector. And so the first argument is just takes in the circuit that you're using, and then and so when you print that, this is basically a matrix that shows the coefficients for each possible state. So in this case, it's the possible states that it's recognizing are 0, 0, 0, where all the qubits are in the 0 state, and then the last one is 1, 1, 1, where all the qubits are in the 1 state. So there are 8 possible states that the system could be in. So the first one represents 0, 0, 0. This second one is 0, but it would be 0, 0, 1, and so on. And then the last one is just 1, 1, 1. But that's another way to sort of get information from the circuit. So it basically allows you to look at the final matrix produced from the circuit. So the next part is sort of an interesting feature that it has, where as long as all of the gates in your circuit are unitary, you are actually able to get a representation of the matrix, the 2 to the n by 2 to the n matrix, where n is equal to the number of qubits. So in this case, the number of qubits we're using is 3. So it would be an 8 by 8 matrix. And so this basically has the 60 entries, and this matrix just represents what all of the gates, multiplied together would look like if you were basically if you multiplied it all out into basically like the full state basically. So that's kind of a useful feature. And so the way you would do this is just, result, you're using the result again, but instead of .get counts or .get state vector, using .get unitary. And again, you just specify the circuit that you're trying to get. And so this can be useful in terms of looking at exactly what matrix your circuit would actually be defined by. The next part is meant to demonstrate. So here, what you can do is you can, is you can add circuits. So if you created a circuit, measure, this is a new circuit, but it still has the same dimensions as the first circuit in that it's like 3 qubits, 3 classical bits. So here we just define, we use a barrier method, and then they just sort of measure it. And so they measure the first 3 qubits using range 3, which just indicates that you would measure all 3 qubits and then map them to range 3, which is just 0, 1, 2. And so that you can create a new circuit that adds the 2 circuits we had before. So in this case, the first part is the circuit, which we had defined above, and then the second part is the measure, which we had just defined. And so it's kind of an interesting thing that you can sort of concatenate, like if you were defining a string where you can add strings and it'll just group them. So the next part is just meant to show the number of counts and how, so we've already kind of gone through this, but again, you can sort of plot the histogram using the plot histogram method, and you would use the values you get from the result.getCounts. And then here's another interesting thing where you can plot the state. So in this case, the method we're using is just, you get your state vector simulator. And so you've got the state vector basically, and then you execute again. And then what you can do is you can, once you've got the state vector, you can plot it. And so using the plot state Q-sphere, you can actually just plot it on a sphere. And so in this case, we have the 2 states, 0, 0, 0 and 1, 1, 1 from the original circuit. So that's just one example of the numerous ways you can represent the circuits. The next thing that I'll talk about is the sort of gates that Qiskit provides. So just sort of starting out, it has, this is the, if everyone can see, this is the matrix form of the general single qubit gate, where it's basically all parameterized in terms of 3 variables, theta, phi, and lambda. And so this is the most general form of a single qubit gate that you can use that's still a unitary. And so Qiskit provides access to that. So the way it would work is you just do QC, which is the circuit, .U3. And so the 3, it's a unitary gate that has 3 variables. And then you would enter the parameters in terms of the first one is theta, the second one is phi, and the third one is lambda. And then the last one would just be the qubit that it's acting on. And so again, we see the draw function, and it just draws the basic gate, but it shows the variables that it has access to. And then the rest of this page just sort of goes through all the gates that you have access to. So you have the identity gate, the NOT gate, where it's just an X. And so, you can sort of go through this on your own time, but it just kind of illustrates how many gates that Qiskit can implement. And so any gate that you really want can be implemented through Qiskit. So again, this is sort of the standard rotation gates, where you would basically have the rotation, and then it has the parameter of the angle by which you're rotating it. And so in this case, it's pi/2. And then this is the qubit that it's acting on. And that goes for all of the other rotation gates. So any sort of gate that has a parameter, you would just enter the parameter and then the qubit that it's acting on. So these are just multi-qubit gates. The next part, so it gives access to any sort of control gate. So any gate that you wanted to condition it on one other qubit, you have access to that. So the control NOT, controlled Y gate, controlled Z, which is basically just, so you have access to all of those. So this page basically just covers all of the possible gates you have. So you have the access to the Toffoli gate as well as the swap gate. But one thing I did wanted to just mention was that there's a reset function. So what you can do is if you've applied a bunch of gates and a state is no longer in the 0 state, what you can do is reset it back to the 0 state. So what you would do is you just take the circuit and then you would reset and you would just choose whichever qubit you wanted to reset. So in this case, Q0 represents the first qubit, and that would just go back to 0 basically. So that's sort of a way to reset any qubits that you wanted to reuse after doing a bunch of operations. Another interesting feature that Qiskit provides is conditional operations. So what this first example shows is you can condition applying the NOT gate on the qubit on what the classical bit is. So in this case, it's always going to be applied because the classical bit is always 0 because nothing's changed it. And so it'll always apply the X gate. But in this case, the second example, it's a 50% chance because once you've applied the Hadamard gate, it puts it into a two-state, like two possible, 0 or 1 with equal probability, and then it measures that. And so there's equal chance that it's in that. Once it measures it, that sets the classical bit to either 0 or 1. And so if there's a 50% chance it's in the 0 state, and so there's a 50% chance that this X gate would be applied. And so that's just an interesting feature where you can condition, quantum gates on the classical bit. And then the last thing I want to mention on this page is just say you don't want to initialize your qubits to 0 or 1. What you can do is you can choose any arbitrary vector. And so in this case, you can choose sort of like just a really, big vector, but basically any state you wanted to start your qubit in, you can do that as long as it's, normalized. And so what you would do is you just make the desired vector that you want your qubit to start in. And then when you're creating the quantum circuit, you would just use the initialize function, and you would take the vector that you've created above, and you would basically apply it. In this case, they're applying it to all the qubits, but you could just specify one or whichever one you do want. And so that's that. Now, the next thing I want to show is composite gates. So in this case, what you can do is this is basically just a larger gate made up of subgates. So the subgates would be the basic gates like Hadamards, S gates, T gates, whatever you want. But basically, it's just you can customize your own form of circuit. So in this case, they create a subcircuit called it's just called subcircuit. And what you can do is you apply. You would apply, like, let's say you want the subcircuit to do a Hadamard gate on the first qubit, and then a controlled rotation around the z-axis gate on 0 and 1, and then you apply a barrier, and then you apply an identity gate, and then you apply. So basically, it's just you create a subcircuit. You can then apply a bunch of different gates into the subcircuit, and then that subcircuit is now defined as those gates which you've just sort of set in it. And so when we look at it, what we can see is this is they create basically a normal circuit, and they apply the H gate, Hadamard gate, and then a controlled NOT, and then another controlled NOT, and they apply the subcircuit. And so this subcircuit is then going to do all of the things that you've encoded in it above. And so it just shows the subcircuit here, but what you can do if you wanted to see the full thing is you can create a new circuit that just is decomposed. So basically what this decompose method does is it'll unwrap all of the sort of like combined gates. So, when we've seen it drawn, this right here, starting after this control NOT gate, is the subcircuit that we just defined above. So you can see the Hadamard gate on the first one, and then the other things that were defined as well. So sort of just, this is an easier way if you are, constantly reusing the same sort of sequence of gates. What you can do is just define a subcircuit for that set of gates, and then you can just sort of reuse that over and over again. And that makes it easier to code. This next part, it's just talking about parameterized circuits. So basically what this means is you can define a variable for all of your like, so in this case, they're just, you take a regular parameter theta, and then you create a circuit. And so they've added Hadamard gates and they've added control not gates. And then they basically, what they do is they apply controlled, or not controlled, but rotation gates with this variable theta. So in this case, it's qc.rz, the theta variable, and then they apply it on all 5 of the qubits. And what that does is it's a general circuit now. So it doesn't have a specified parameter. So it doesn't have like pi over 2 or like a set number. But what this allows you to do is you can then create like a theta range, or basically just like values which theta could take. And so you would use, in this case, they just use numpy and create an array of values from 0 to 2 pi. And there are 128 values like in between. So it's basically just 0 to 2 pi with 2 pi over 128 instances. And so what you can do is you can set the circuit to, you basically create a bunch of new circuits where each circuit in the circuit array has a specified theta value. So in this case, one of the circuit values is the one with 2 pi. So it basically creates an array of circuits where each circuit has a different theta value. And the theta values are determined by this, just an array of values. It could be whatever you want. But that's just a way to, that's just sort of an interesting thing. Now, in terms of visualizing quantum circuits, so this is, I kind of talked about this a little bit before, but there are a couple of ways to draw them. So the first way is sort of the most basic. You're just printing the circuit. So you've defined a circuit above, but then when you print it, you're just using this basic print method, and it sort of doesn't look very clean. It's not, it looks okay, but it's definitely not, ideal. But another way you can do it is using the draw method. And in this case, it doesn't have the output equals MPL, but it should, but it just looks a lot like a much cleaner. And so you can easily visualize the circuit that you've just created. So, it shows the Hadamard gate, the NOT gate, as well as the measurements and which classical bit the measurements are going to. So this number here, the 2, represents that the second qubit has gone to the second classical bit, and, et cetera. And then another way is, and so basically what this draw method is doing is it's taking the matplotlib, which is just another sort of like numpy, another way to render circuits. And then another way to do this is to use the LaTeX version. And so hopefully when I run this, it should work. But yeah, this is the LaTeX version of this circuit. And so it's just a different way to look at it. You can kind of choose whichever preference you want. But in my opinion, the matplotlib one looks better. But it's just, you have multiple ways of looking at circuits. The next part is you can just sort of, invert the way the circuit diagram is represented. So in this case, you have a circuit that, goes straight down, the first qubit, second qubit, third qubit, et cetera. But what you can do is using the reverse bits method, when you're drawing the circuit, what you can do, it just flips the circuit diagram. So in this case, the first classical bit is on the bottom, and then it goes, the second classical bit is on the top. And same with the qubits, QA naught, which was, as you can see at the top, is now on the bottom. And so that's just another way you can sort of rearrange or get a different feel for the values. And the next thing I'm going to move on to is just how the qubits are actually implemented. So in the beginning, when I showed the diagram of the qubit connectivity, what that is it's a coupling map, and it shows how the qubits are coupled. And so in this case, you can't, so like certain actions by the circuit aren't allowed, in that you can't have like a controlled NOT gate between 2 qubits that aren't coupled. And so what they'll show is basically, if we get down to this example, this C0, like the C0s here in this circuit diagram, you wouldn't necessarily be able to actually execute this on a real device, depending on what the coupling map is, because it's possible that the first qubit and the 6th qubit aren't actually coupled, and so you wouldn't be able to do a C0 there. And so what you can do is using what's basically called a pass manager, but it'll show you how exactly the quantum machine is interpreting it. So the first one that'll show is just the basic swap, which just basically shows sort of a simple way that the machine can do the C0 like operation here, even if these aren't coupled. And so what that might look like is you just perform a bunch of swaps. And so you would perform a bunch, like a swap between these two, and then you would swap these two. And then what you get is Q0 is now where Q5 is. And so then you can perform a C0 because those two are coupled, and then you can do whatever you want. And then, that sort of also applies with the C0 here, where you're not able to do it between those two. But after the swaps, you can. And so this is, using what's called the basic swap, coupling map equals, coupling map. You can just sort of show, it just shows you exactly how the machine is interpreting it. And there are other ways to represent it. So this is a condensed version, or a different way of, it's a more efficient way of doing the swap. So instead of going through and doing this one, only doing the swaps, you can just do Q6 can move up and Q0 can move down at the same time. And so that's just meant to shorten the depth of the circuit, because you're able to compute swaps at the same time, as opposed to, waiting for each swap to execute in this one. So this is just a more efficient way. And so this is all sort of meant to show that, this is like a way you can understand how the machine is actually interpreting your code, and how it's like actually performing the operations. The next part is, this is just sort of a quick reference. There are optimization methods in Qiskit. So let's say you created a quantum circuit, but you wanted to optimize it, or shorten the gate count, or minimize the depth of the circuit. What you can do is, you have various optimization levels. So for 0, it just doesn't do anything to the circuit. It doesn't apply any optimization procedures. But for optimization level 1, it does lightweight optimization. So basically it will look for any redundant gates. So if you have 2 gates that are next to each other that are the same, so if you had 2 Hadamards, those would cancel out. And so, it just sort of goes through and looks for easy optimizations. And then optimization level 2 and 3 are, it does more complex things. And so the way you would implement that is you would just, when you've created your circuit, you would just apply optimization level, I think it's around here, but basically you would just be able to apply that whenever you're, finished compiling. So sort of so let me try and find that. But so right here where optimize 0, so you would use the transpile method. And so you would take the circuit, you would take the backend, or the device that you've defined that you want to run the circuit on, and then you would define the optimization level right here. So in this case, they're not doing any optimization because they're choosing optimization level 0, but you could easily switch that out for anything. And so just sort of a demonstration of how versatile Qiskit is in terms of the things that you can do with your circuits. So you can optimize it, you can see how the machine is interpreting it. And so, so now this example circuit, I think I've already basically gone through that. I think what I'm going to switch to now is sort of going over the tools. So this is this is how you would actually implement stuff. So first, the results page. It's not super complex. It just has sort of, it shows pending jobs. So this would be if your circuit takes a long time to run, or maybe it was put in a queue of it had a long queue time. So maybe your circuit was the 50th on a certain device, then maybe it's pending. And so it gives you the status. It gives you when when you started running it. And then it also has a list of completed jobs. And so you can just sort of use this to organize and go through what circuits you've already run and look at previous results. But overall, this page doesn't really have super interesting information. It's just, if you're running circuits, this is where you would find it. But the circuit composer is sort of the most like interesting thing. And, for beginning programmers, if the coding part of it is difficult for you, this definitely makes it much easier, because all you really have to do is, drag and drop the gates where you want them to. So the first bar, at the top, you just sort of, see the usual file and edit. And so this is where you would, save your circuit. Here you can name what circuit you want it to be. So, trial circuit. And so that's where you would name it. And so, but then the interesting part becomes when you start adding gates. So if you just apply, any basic gate, T gate, let's say S gate, what you can do is you can use this inspect function, and you can go through and look at the state of the qubit as it's being like applied. So you can click on this gate, and then you can sort of see exactly what the state is as it's being applied. So in this case, if we go back and we add, like a Toffoli gate and a Hadamard, and we delete these gates, what you can do is you can just see, using the inspect function, exactly what. So in this case, the Toffoli doesn't do anything because they're all in the 0 state. So the controls won't activate the NOT gate. But if you go to the Hadamard, you can look at exactly what's happening. So this sort of gives you the state of the first qubit. And so it tells you, the probability of it being in the 1 state is 50%, and, vice versa, the probability of it being in the 0 state is also, just 50%, because, you would just subtract the probabilities. And then, so this is just an interesting tool that you can use to really get at the basic level, like what your circuit.
Uh-oh, something happened. So hopefully Ian can reconnect. Everybody still able to hear me? Okay, so something just, maybe he was taking too much bandwidth or something. I hope he will be able to restart. So those of you guys who are in the room, we will post the materials on Slack. Is everybody on Slack? Those people who are still here? Yeah, I know that Javier is. Raphael and Mazen, if you want to get a hold of these materials, I certainly recommend that you join. Do you have the link for Slack? Okay. So I see that Ian is joining back, so he should be able to restart quickly.
I'm so sorry about that.
No
My
problem.
computer died. Sorry.
Oh.
Yeah, that's what happened. So I'll get right back into it.
Oh, you have a backup. That's great. Well prepared.
Yeah.
Okay, go ahead.
Oh, actually, I think you need to make me the host.
Oh, I'm sorry about that. That's correct. Co-host. Here you go.
All right. So yeah, going back to the inspect function basically just lets you sort of get into the nitty gritty of what your circuit is doing, live. And so you can kind of go through at the basic gate level, what state your qubits are in. Something else you can do is using the view function, you can sort of click on and off various representations of the circuit. So if you, wanted to see, if you didn't want to see the Q-sphere, or if you didn't want to see the measurement probabilities, you could just click those away. But, at the same time, you can just, it does give you the option of seeing them. So you can see the probability that the state, in this case, it's 3 qubits, the probability that the state is in 0, 0, or that the state is in 0, 0, 1. And so it gives you that right there. It also gives you the state vector. And so these would be the coefficients of the various states. And so it can either be in 0, 0, 0 or 0, 0, 1. And so those are sort of different representations that you can sort of visualize the circuit as. And in terms of the way you would actually construct your circuits is you would just drag and drop, whichever gate you want. So here we have sort of the basic gates, the rotation gates, and then the control gates. And then something interesting that you can do is you can add customized gates. So it gave me this little pop-up to create a new operation. But what you can do is, this is sort of a generic, it's called just NGO, but if you go over to this code editor, it shows up right here. And so when you add it, it'll just, let's say if we just add it here, it'll show up on the code editor right here. So the first gate was the Toffoli, and so that's represented as a CCX, and then the, control target bit. And then there's a Hadamard gate, and then there's a T gate. And so it specifies which qubits those are acting on. And then this one shows up where it's a customized gate. And so you can change the parameter of what it does. But basically this is just, you can make any new operation whatever you want it to be. And so the way you would define it is just by coding it in OpenCASM, which I'm not super familiar with how to, the coding language that they use for that, but you would just be able to edit it to be whatever you want it to be. And then once you've done that, it would just edit, and then you would have that gate to customize. So one last thing is, when you're finished making your circuit and you want to actually run it, what you can do is you would click on Run Settings, and you can choose the actual machine that you want to run it on. So in this case, if you want to choose the actual, like an actual quantum device, you would just click on that. And then the provider is, the provider doesn't really matter. And then you could choose the number of shots that you want to have the machine use, or the number of times you want to have the machine run. And then you would just run, and then, okay, so in this case, yeah, it requires a measurement. But yeah, the way you would do that is just using this, which is the measurement. And so for all of these gates, it gives you, it specifies exactly what gate it is. And so you would just do that, and then you can run it. And then it would show on the jobs area exactly like where it had been done. So in this case, it's actually queued. And so this is sort of interesting because it says that it's going to run probably in an hour. So that just sort of goes to show, if there is a long queue, it may take some time for your circuit to run. And so it's not going to be an immediate thing necessarily. Now, if you use the quantum simulator, you shouldn't really have that issue. It should be able to run immediately. Yeah, so it's running. And then once it's done running, yeah, it says it's completed. And so if you click on that, you would be able to see exactly what it had done once it loads. So it gives you the time taken to run, and then it also just gives you the measurements that it got, as well as it shows you the circuit that you made, as well as how the machine interpreted it. So in this case, the custom gate is really just a Hadamard gate, so it doesn't really change much. So it just basically translates it. So if the custom gate were a little bit more complex or had more basic gates inside of it, then those would show up here, because it would basically sort of decompose the custom gate. But going back, so that's how you would run any circuits that you make. And so you would be able to see them here on the jobs place. And then anything that I haven't covered in terms of the circuit composer, you can use Qiskit's guided tour. And so if you click on that, you basically are just given sort of a comprehensive overview of like the tools you have access to and how to use them. And then, yeah, and that's sort of wraps up the presentation. But basically the key thing to take away is like Qiskit has, basically a step-by-step tutorial for everything you might want to know. So, for each of the things for the circuit composer, if you're in the docs area, it has an overview, goes through creating the first one, the building and editing process. So for anything that I didn't cover in this talk, you can easily go and, they have a very step-by-step, easy to learn process for understanding it. And for, beginner quantum computing folks, it also, gives you a good understanding of like what it is. It talks about the start out, just, a basic qubit and then creating superpositions. So it goes through. And then one last thing I want to highlight is just for anything that basically the comprehensive area where you would find everything that Qiskit has to offer is this documentation page where they go through, they have tutorials for everything you might need. So in this case, I really only focus on circuits and some of the advanced circuits, but there's a lot of other things that Qiskit has like access to. So, this pulse is like, you can control the actual like photons that are energizing or, putting the qubits into a superposition state. And so you have access to that. They also have, tutorials on a bunch of other things as well as the applications. So basically everything that you could want to know about Qiskit, it has, it's all well contained and very easy to use. And they also have a free textbook that you can access that goes through the, starting from the very basics of just a basic qubit to, very advanced algorithms. So that's sort of all I had in terms of the presentation. I'm open for questions. Yeah.
Great, thank you so much, Ian. That was great presentation, and you managed the almost impossible task of fitting it into 1 hour, which is amazing. Yeah. There were a couple of questions. We won't have time for a long discussion, but Raphael, do you want to unmute and ask your question, or would you prefer me to ask it? So Raphael was asking about whether or not the code editor outputs the Python code directly.
So when you say code editor, do you mean the Quantum Lab or the?
I meant that visual editor that you showed, which outputted QASM.
Oh, okay, yeah. So that would be the circuit composer.
So you can just copy it into the Jupyter, I guess, then?
Yes. So what you can do is it shows both the QASM and Qiskit. So yeah. So you can only edit the QASM. So that's where, if you added a custom gate, you could edit the custom gate. But it does have a read-only version of Qiskit, where if you created the circuit, it would create the code, and then you would just copy and paste. So if you add like an S gate and it adds it here, and so you could just, you could just as easily copy and paste that onto a Jupyter notebook in the Quantum Lab.
Yeah, thanks a lot, and really great presentation. Thank you very much.
There was another question from Raphael early on about if you have favorite examples using Qiskit or idea of applications and exciting applications people could start with.
Yeah, so so first of all, for any sort of tutorials for those kinds of things, they have it if you go to the Quantum Lab right here. But the primary applications would be for optimization, as well as they have a chemistry-based one, but mostly optimization and algorithms. So in this case, a Grover algorithm to like Grover search function, but they also have other things for, in this case, you can see they have things for quadratics, and then it's primarily optimization is where you would do that. But for any of these tutorials, even if you have like absolutely no understanding, once you click on it, it goes through and does a very comprehensive tutorial of the program. So once this loads, and hopefully that's soon, you can, but basically you can, use the tutorials, and then it'll teach you everything you might want to know. Another one is, aside from optimization, is there are some chemistry examples where you can find, the energy of certain molecules or certain elements at in certain conditions. But yeah, and so it is taking somewhat of a while, but yeah, so it, just starts from a basic, it just sort of goes through the application here from the yeah, so we briefly introduced how to build optimization problems using Qiskit's optimization module. So, you know, I have not really used these as much. I've mostly been focused on just using the like making circuits. So I haven't looked at the applications too much. But the tutorials that Qiskit gives you access to explain it pretty well, where they sort of go through each step and provide an explanation of each step. But yeah, I would direct you towards the Qiskit tutorials, and that's where I would send you.
Sounds great. I have a question. In your experience, how long does it take to run it on the actual machine? So these queues, how bad are they?
Yeah, so I was actually kind of surprised. I didn't think I have not ever. Usually, it's not an hour. I think an hour is probably the upper limit. I think the reason that was because there was a queue of like 50 jobs. So I think, but usually it's like, you know, only like 5 minutes, like maximum. Like if you get a device that doesn't really have, you know, maybe like 1 or 2 jobs, usually it doesn't take that long. I will say, you know, you don't necessarily, like, unless you don't necessarily need to use the real device. Like if you're just sort of trying something out, the simulator is also a great tool, and that is like, I think it's guaranteed to always be, you know, I don't think there's a queue for the simulator. I think you can just use it and it'll run right away. But usually it shouldn't take an hour. Yeah.
Sounds good. Are there any other questions? Right, so I will stop the recording and